All right, so now we move on to Chapter 7, Section 2. Up to this point, we have been talking about right triangles. Even when we built our angle off of our unit circle, we were dropping a perpendicular to the x-axis, so we were still focusing on basically an angle that was part of a right triangle. But not all triangles are right triangles. If there is no right angle, then we have an oblique triangle, and that just literally means not right. So these triangles can either be acute triangles because they have all acute angles, or only have two acute angles and one obtuse angle and be called an obtuse triangle. Now, you can't have more than one obtuse angle because obtuse is greater than 90 degrees. So once we have drawn an angle that is 90 degrees or greater, that means the others have to be acute. Now, when I have oblique triangles, there are 4 different cases that I could end up with. We noted in Section 1 that we were given 3 pieces of information. One of those pieces of information was the right angle. Well, we're still going to be given 3 pieces of information. It matters whether you're given 2 angles and 1 side, 2 sides and 1 angle, or all 3 sides. Now you can see the way these are highlighted that in this section we're going to talk about cases 1 and 2, and in the next section we'll talk about cases 3 and 4. Typically, if we were in class, we would have a neat investigation we would do here where we would work in a group and we would discover our law of signs that we're going to be focusing on, and we would have some manipulatives to use, but we're just going to kind of do the best we can. Our first case, either angle, side angle, or side angle, angle, you could call it either way because order doesn't matter, is when I know one side and any 2 angles. So it doesn't matter what order that side and those 2 angles are in. This implies that we have a side between 2 angles. So for example, if this is my triangle, and label your triangle carefully so that the appropriate sides are opposite the appropriate angles. If this is my triangle and I knew angle, side, angle, it would imply that I knew angle, side, angle. So the side that was included between those 2 angles. Or side, angle, angle would imply that I knew, for example, side B, but angle A and B. So this side is not included between those 2 angles. Doesn't make any difference. That's case 1. Our second case is what we call our ambiguous case. It's when we know 2 sides and an angle opposite. So if I know 2 sides and 1 angle opposite one of those 2 sides, that is my side-side angle. This is my ambiguous case. And you can remember which one is the ambiguous case because if you write this backwards, it is a pain in the, because you don't know how many triangles you have. You could have 0, 1, or 2 triangles that can be formed from your given measurements. It depends on how the measurements are given. And then the other 2 cases that we're not going to address in this section are when I know 2 sides and the included angle, 2 sides and included angle, or when I know 3 sides. Okay, so let's talk about using the law of signs to solve cases 1 and 2. The law of signs theorem tells me that for any triangle labeled ABC correctly, I know that I have a ratio that I can count on. That the proportion, if I set up each ratio as the sine of an angle compared to its opposite side, any 2 of these pairs, any 2 of these rates or ratios will be proportional. So these 2 ratios will always be equal. These 2 will always be equal. These 2 will always be equal, as long as I have labeled my triangle correctly. Now, in addition, I use the fact that the sum of the angles in a triangle will always be 180 degrees. Now let's do a little bit of an exploration or a proof of this law of signs. This sketch is a triangle with 3 acute angles. We're going to look on the next page at an example of a sketch where I have an obtuse triangle instead of an acute triangle. Now this triangle is drawn, triangle ABC is drawn to look like it's pretty much equilateral. That really doesn't matter. We're just showing you that this is going to work no matter what the shape of the triangle. Okay, so first thing we're going to focus on is A. The sine of A. Remember, sine is opposite over hypotenuse. Well, this is a right angle. This is marked as a right angle, so I'm just looking at this smaller piece of our acute triangle. I have a right triangle here, and the sine of angle A is going to be h over c, because opposite over hypotenuse. So sine of A is h over c. What about sine of C? Well, here's angle C, and if I look at just at this piece, I see that the height of the triangle H, sine of C would be h over A. Solve each ratio for H. So I'm going to take this ratio and rearrange terms so that it's set equal to H. I'm just going to multiply C by both sides. So H equals C times the sine of A, and for the second one, H would equal A times the sine of C. Now, since the height H referred to in both of these ratios is the same measurement, H can be set equal to itself, correct? H is equal to itself. That means that C sine of A, C times the sine of A, is equal to A times the sine of C. Now I can just rearrange terms. If I divide out the A, that cancels here. And then if I divide both sides by C, that cancels here. I'm left with sine of A over A is equal to sine of C over C. Now if I turn my triangle and constructed another altitude, I can do it and find the pair that went for sine of B, B as well. But we're not going to do that. We're just going to show you, look, we can use measurements given to prove our law of sines for an acute triangle. Now the next page in our notes does the same type proof with an obtuse triangle. So you see your triangle ABC here, ABC, where A is an obtuse angle, B and C are acute angles. I can draw the height of this triangle just like I did the acute triangle, but this time the height doesn't go inside because of the obtuse angle. From the difference formula for the sine function, it can be shown that the sine of this angle right here is 180 degrees minus A. So whatever A is, this is the rest of that straight angle. So 180 minus A. The sine of this angle is going to be opposite over hypotenuse. So h over c. But if we use the difference formula, we can calculate it as sine of 180 degrees, difference formula. This is sine the difference formula. I'm so sorry. The sine difference identity. Sine of 180 cosine of A minus cosine of 180 sine of A. That's one of my sum and difference identities. I'm used to teaching from a book that calls these identities instead of formulas, and it threw me. If I use the sine difference identity, sine of 180 cosine A minus cosine 180 sine A. Well, the sine of 180 degrees, think about your unit circle. The sine of 180 degrees is 0. Cosine of 180 is a -1. So I have 0 minus a negative sine A, which gives me a positive sine of A. And then, like I just said, sine of A is, if that is the same as the sine of 180 minus A, then that is going to be h over c. Now, if we set this result up just like we did the last page, both of those set up to be sine of A was h over c, and then I did sine of c and I got h over A. If I kept going for these, I would see sine of c is h over A right here. Sine of c is opposite over hypotenuse. And I could complete my proportion with the obtuse triangle. Okay, So that was just proving to you that the law of sines works. Now let's use our law of sines to solve for a triangle where we know 2 angles and 1 side. It doesn't matter if that side is included or not. Now when I'm solving these triangles, I need to remember to sketch first. It really helps to have a correctly labeled sketch. So sketch first and label carefully. Now, always before, we've been sketching right triangles, and we made sure that we labeled our right angle as C. These are oblique triangles. They're not right triangles, so it doesn't really matter what shape your triangle is, but you're going to have A, B, C, and then the sides opposite carry that name. So the side opposite angle A is side A, opposite angle A is side C, opposite angle B is side B. Now let's look and see what information we are given. We know that angle A is 20 degrees. We're told that angle B is 80 degrees. And we're told that side A is 4, and we're not given units. So we have angle, angle, side. Angle, angle, side. When I'm given the choice, remember to always use your given values instead of found values to solve, because you might have made a mistake. So found values could be wrong if you made a mistake. And usually if it's a found value, it's an approximation, not exact. So you are compounding your error, your approximation, anytime you use a found value. So remember, we're going to solve this triangle. We're given 3 pieces of information. We want to find the other 3. We are given 2 angles. We need to find 1, and we need to find our 2 remaining side lengths. Well, angle C is easy because the sum of the angles of any triangle is 180. If I have 80 and 20, that's 100, so angle C is going to be 80 degrees. Now let's find side B and side C. Those are the 2 side measures that I don't know yet, so let's find those. I'm going to use my given information and law of sines. Law of sines says that I have sine A over A equals sine B over B equals sine C over C, and I can flip those. I could write it as A over sine A equals B over sine B equals C over sine C. Either direction, law of sines works. So let's see what pair we know. Well, we know A. We know sine of 20 degrees over 4. I can solve for side B. Sine of 80 degrees, angle B, over side B. To solve a proportion, I find cross products. So I have B times the sine of 20 degrees equals 4 times the sine of 80 degrees. And then I need to divide both sides by the sine of 20 degrees to finish solving for B. Now we're going to solve for B. We're going to round, let's just round to a single decimal place here. What I input into my calculator, 4 times the sine of 80 degrees divided by the sine of 20 degrees. Let me get the glare off my screen. All right, we're in degree mode. Make sure you check. 4 times the sine of 80 degrees. And then I take that and I divide it by the sine of 20 degrees. And I get a side length for side B as 11.5. And I don't have units. So that's that. Now, the other side length I need is side C. What is something you notice here, hopefully, when you start to set this up? Well, I'm going to start with the pair I know both pieces for. Sine of 20 degrees over 4. Angle C. Angle C is also 80 degrees. So when I go to solve for side C, it's going to be the same as side B because this is an isosceles triangle. An isosceles triangle has 2 equal sides, which means it has 2 equal angles. So when I know that I have two equal angles, I know that these two sides are going to have the same measure. Okay, so we know all three sides, we know all three angles, our triangle is solved. Let's go ahead and look at the next page. We've been given another triangle to solve. Let's sketch our triangle. You always start with an appropriately labeled sketch. We have side A, side B, side C. Let's fill in what we know. We know angle B is 25 degrees. We know angle C is 85 degrees. And we know side A is 6. Now, I know that my lowercase b's and my 6's look a lot alike. I've worked really hard to try to fix it. I can't fix it. I don't know a way, so just pay attention. I know two angles and a side, and my side this time is included between the two angles. So this is angle, side, angle. That order is important. We always want to recognize when we have what order we have things in. So we have angle, side, angle. Well, I know two angles. That third angle is easy because the sum, the third angle is easy because the sum of the angles in a triangle always add to 180. So if I already have 85 and 25, that's 110, which means angle A has to be 70 degrees. This triangle is not isosceles. This triangle is going to be scalene. All my angles are different, which means all my sides are going to be different. So I need to solve for side C and side B. The pair I know, I have to use this found value, but it's not a guess because we know that we add to 180, so we're okay. I know that sine of A, so sine of 70 degrees over 6, that's the pair I know, is going to be equal to sine of 25 degrees over B, and then I can solve for C by saying what I know, the pair I know, sine of 70 degrees over 6 would be equal to sine of 85 degrees over side C. So these are the two things I need to solve. Now we said we know all three side lengths are going to be different. Which side is going to be the longest? Well, my longest side is opposite my largest angle. So side C is going to be my longest side. Which side will be shortest? Well, side B will be shortest because it is opposite my smallest angle. Notice that our triangle is not sketched to scale. That's fine. Okay, so we have 6 here as a numeral, and that's a B under 25 degrees. So B is going to be equal to, if I multiply 6 times sine of 25 degrees over sine of 70 degrees. That's how I solve for the length of side B. Plugging that into your calculator. This time I chose to round to 2 decimal places. So go ahead and do that for me. Round to 2 decimal places. I've got 2.70 as the length of side B. Over here for side C, I would do cross products and then divide out that sine of 70. So I have 6 times the sine of 85 degrees over sine of 70 degrees. And that gives me the length approximately of side C as 6.36 because I recorded 2 decimal places here. My math lab will give you instruction. I try to be very clear on tests to give you instruction as far as rounding. All right, side angle. This is our ambiguous case, guys. This is our ambiguous case. Ambiguous means, it might be this, it might be that. There are 3 different ways this can fall out. There could be 1 triangle, there could be 2 triangles, or there could be 0 triangles with the given measurements when I'm given 2 sides and an angle that is not included between those 2 sides. A, B, C. We know that B is 35 degrees. We know that side B is 5, and we know that side A is 3. So we have angle side or side angle depending on which way you want it to go, but it's going to be a pain. We've got to check. We've got to figure out how many solutions we're going to have. When we have this case, you have to check to see if there's a second solution. When you're given side angle, you must check for a second triangle. You have to check for a second triangle. When you are given side-side angle, those are the three pieces of information you're starting with. You have to check to see if there's going to be a second triangle or not. I've only been given one angle, so I can't magically come up with these other two. I have to use what I know. So what I know is angle B and side B. So I'm going to start by saying sine of 35 degrees over 5. That's my starting place. Well, the only other piece of information I have is this 3. So I need to solve for angle C. So that is going to be equal to the sine of angle C over 3. That's where I have to start. So let's solve for this sine of, did I set this up? I totally set this up wrong, guys. Dadgummit, I'm so glad I caught myself there. Have you been yelling at me? What did I do wrong? I mislabeled my triangle. So let's go back and fix that. Side A is 3, not side C, which means when I'm setting this up, I'm solving for A, not C. That absolutely matters. That would have made a world of difference at the end. Okay, so angle A, side A. Angle B, side B. Angle C, side C. We don't know side C. So we're starting by finding angle A that is opposite side A, which is 3. I know this pair. I'm solving for A. So here we go. I've got it set up correctly now. Sine of A equals 3 times the sine of 35 degrees over 5. I'm going to simplify this, not round it off, and then take sine inverse to solve for angle A. So I will find this value and then take sine inverse. When I do that, I solve for angle A. So let's do that. So we have 3 sine of 35 degrees, 3 sine of 35 degrees, and then divided by 5. And I get this 0.3444. I'm not going to 344, etc. I'm not going to round that off. I'm just going to say sine inverse of that answer. So I'm going to push second answer, and it pulls that answer back up in its entirety, not rounded, so that I don't round too soon. This is what I get. Now we're going to go ahead and round to 2 decimal places here so that I have 20.13 degrees. Angle A is 20.13 degrees. So we know 2 angles. Let's find the third angle. Angle C is going to be 35 plus 20.13. That sum subtracted from 180. So it's going to be 180 minus 35 minus that 20.13. Angle C comes out to be 124.87 degrees. So we have 2 sides, 1, 2, 3 angles known. We need to solve for our third side. We need to solve for side C. So we found angle A, we found angle C. Now we need to find side C. So we go back to our known pair for our law of sines. Sine of 35 degrees over 5 is going to be sine of, we have to use the found value here, over side C. So side C is going to be 5 times the sine of 124.87 degrees divided by the sine of 35 degrees. Side C is about 7.15 when I round to 2 decimal places. Remember to pause this video so you have time to catch up. Okay, that's my first triangle. Is there a second? I'm still waiting to see how many solutions I have. I know I have one solution. Do I have a second solution? Well, let's go back and see. Remember that when I use sine inverse is restricted to quadrants 4 and 1. if it's a positive sine function value, it gives me an angle in quadrant 1, right? So I got this angle. There is another angle over here in quadrant 2 that has the same sine function value. This was angle A, the first angle A. Is there a second value possible for angle A? Do I have an A sub 2? Well, if I do, it's going to be 180 minus whatever this was, because it would be a full over here to pi to 180 degrees minus what this original value was. So let's see. If there's a second A, it would be 180 minus 20.13. So if there's a second triangle, the measure of its angle A would be 159.87 degrees. Does that work? Well, remember we were given angle B. Angle B is 35. So if I add in angle B, oh, that's already more than 180, right? That's 194.87 degrees. So I have no second triangle because that is more than my possible sum for the angles in a triangle. Second angle A won't work, so I only have one solution in this ambiguous case. All right, let's look at another one. Side-side angle, that's my ambiguous case. How many solutions does this one have? Let's check it out. Sketch our triangle, and I'm going to do a better job of labeling this time. Angle C is 15 degrees. Side C is 6. That's the pair I know. Side A is 10. So I've got side-side angle. This is ambiguous. I could have 0, I could have 2, I could have 1. I don't know yet. Let's start with a pair I know. I know my C's. So I know sine of 15 degrees over 6. And then the next thing I need to solve for is angle A because I know the side opposite it. So sine of A over 10. That means sine of A, when I solve my proportion, is 10 times sine of 15 degrees divided by 6. I'm going to find that value, and I'm going to take sine inverse of that to find the value of angle A. When I put this into my calculator, I should get about 0.43. I'm not going to round it off. So I have 10 times the sine of 15 degrees divided by 6. Yep, that's what I get. I'm not going to round that. I'm going to take sine inverse and have it pull that answer back for me. Second answer. My answer button is right here. Second answer, second function answer, enter. That's my angle measure for angle A, my first angle A, 25.55, excuse me, 25.55. Okay, so it doesn't give us any instruction, does it? 25.55 degrees. So that's my angle A. Well, we know angle C. What's angle B here? Well, 25.55 plus 15 is 40.55. So that means angle B would be 139. Out of 180 is going to be 139.45 degrees. So that's my angle B. Okay, we know one side, all three angles. We need to solve for the other two sides. Let's start by finding, oh no, we just need one more side. We need side B. So we go back to the given pair we have, sine of 15 degrees over 6, and we need to solve for side B. So this is my first triangle. I usually go ahead and label A sub 1, B sub 1, B sub 1, and this is going to be sine of 139.45. So what's the measure when I plug that in of this side B? It should come out to about 15.09. Okay, that is one solution. Is there a second? Remember, when we have the ambiguous case, we always have to check and see, is there a second triangle? Well, if there's a second triangle, then that first angle we found will have another solution, because here we found A is 25.55 degrees. What is the angle over here in quadrant 2 that has that same measure? Well, it's going to be 180 minus 25.55. So 180 minus 25.55 comes out to be 180 minus 25.55 comes out to be 154.45. 154.45. If I have a second triangle, that is the measure of angle A for that second triangle. Is it going to work? Well, I was given angle C. Angle C is 15. It's going to work. Look at that. That comes out to be 169.45. So there's some degrees left over. My second triangle is going to work. There's some degrees left over for a second angle B. If A plus B is 169.45, then this angle C is going to be 180 minus 169.45. So it's going to be 10.55 degrees. So I do have two triangles. These two triangles have the same measure for angle C, and side A. They have different values for angle A, angle B. I was given C that time, sorry. And side B. What is side B going to be in this case? Well, it's going to be sine of 15 degrees over 6 equals sine of 10.55 over side B. And that should come out to be, when you plug that into your calculator and solve, 4.26. All right, guys, I'm trying really hard to catch all my mistakes. I like it when I'm in a classroom and you are catching my mistakes in real time. We're doing the best we can without me having a class to catch my mistakes as we go. So that triangle, ambiguous case, had two solutions. We did one with one solution. We've done one with two solutions. Let's see how many this one has. So we sketch our triangle ABC. We're given angle A is 50 degrees. We're given side B is 8, and we're given side A is 5. So it's angle or side angle. We know it's ambiguous. Let's set up and see what we've got. Our pair, we know sine of 50 degrees over 5 is going to be equal to, we have to go for B. So sine of B over 8. So that gives me sine of B equals 8 times the sine of 50 degrees over 5. Let's do that. We do 8 times the sine of 50, I'm in degrees, divided by 5. I get 1.02. 8 times, did I do that right? Oh, I divided by 6. Let's do it again. 8 times the sine of 50 degrees divided by 5, not 6. I get 1.22567. Now, what am I going to do next to solve for angle B? Well, I'm going to take the inverse sine of that. Anybody notice an issue here? What are my possible sine function values? When I take inverse sine of that answer, domain error. I can't have a sine function value that is beyond that 1 to negative 1. This comes out to be about 1.23. That is beyond the range of sine, which means it's beyond the domain of sine inverse, and there is no solution to this triangle. I don't have any triangles with those given measurements. It's not going to work. It's going to be that case where that other side is just too short. Okay, let's look at our last page of notes here. We have a couple of application problems. John needs to figure out how tall the tree is before he cuts it down, because he wants to make sure it's not going to hit the fence. That makes sense, right? Angle of elevation of the tree from one position on a flat path is 40 degrees. And from a second position 20 feet further on, it's 30 degrees. So we're making two right triangles that we can compare. So we've got our tree. Trees don't have to be pretty, right? We just need a sketch to look at. From the top of the tree, the height of the tree, to this point here, my angle of elevation is 40 degrees. From the top of the tree to a point further back, 20 feet further back, the angle of elevation is 30 degrees. How tall is the tree? Well, what have we got here? I don't have enough information to use my right triangles because I don't know this distance. But let's think about what we do know. We know this angle and this side. And you know what? If this is 40 degrees, what is this angle? Because that makes a straight angle. This would be 140 degrees. And that makes this angle 10 degrees. We have a triangle we can solve. What are we needing to know? We're needing to know this height of this tree. But if we can solve for one of these, we can solve inside this triangle. So let's solve for this. Let's solve for this side B. Using our law of sines, we know that the sine of 10 degrees over 20 is equal to the sine of 30 degrees over that side B. So I know that side B is going to be equal to 20 sine of 30 degrees over sine of 10 degrees. And when I plug that into my calculator, I get that this side B right here is, let's go ahead and round that to 57.59 feet. We're going to round to the nearest foot for the height of our tree, but we're not gonna round too soon. So this side is about 57.59 feet. Now I can solve for h using this right triangle. Sine is opposite over hypotenuse, and that's the hypotenuse of this 40 degrees. So sine of 40 degrees is h over 57.59. Or I could just keep that in my calculator and not have to round it off, right? If I multiply both of those times 57.59, I get that the height of my tree should round to about 37 feet. And then I can check and see how far away from the fence it is. Okay. Here we go, last application problem on 7.2. Two fire stations are located a half mile apart, and it gives us the length of 1 mile at points A and B. There's a forest fire at point C, and it gives me a measure of angle B inside the triangle is 41 degrees. Okay, so let's start our sketch. We've got two fire stations, A and B, and they are a half a mile apart. So we can either do feet or we can do miles. I'm looking to see if it needs to, you know what we can do. We can do miles. We can just say this is a half a mile, 0.5 mile apart. Okay, and there's a triangle there's a fire up here at C so that it forms a triangle. And when it forms that triangle, angle B is 41 degrees and angle A is 47 degrees. And we know side C. We need to figure out angle C. Now it says justify how you know without any computations that A is closer to the fire than B. How would I know that A is closer to the fire than B? Well, I've got side B here and side A there. Side A is going to be longer than side B. Side B will be shorter than side A. So this is how far away B is from the fire. This is how far away A is from the fire. So because side B is shorter than side A, it's opposite a smaller angle. That tells me why station A is closer to the fire. Use law of sines to calculate to the nearest tenth how much closer fire station A is to the fire than fire station B. All right, well, what's angle C? If this is 47 and this is 41, we know angle C is going to be 92 degrees because they have to add to 180. So the sine of 92 degrees over 0.5 is going to be equal to the sine of 47 degrees over A, and the sine of 92 degrees over 0.5 is going to be equal to the sine of 41 degrees over B. If I plug that in, I see that fire station A is 0.366 miles away from the fire, and fire station B is about 0.263 miles away from the fire. The question is how much closer A is than B. So I need to compare these two. And I see that station A is 1/10 of a mile closer to the fire than station B.